The topic for this lesson is magnets, magnetic fields, and magnetic flux density. A type of material found in Asia Minor called magnetite gave rise to the word magnet. Since these natural rocks, when freely suspended, pointed north and south, they were used by early navigators who called them lodestones or leading stones. Artificial magnets have now replaced these natural magnets. They are mainly made from alloys, one of them being alnico, which is composed of aluminum, cobalt, and nickel. A substance, when magnetized, retains a large amount of its magnetic strength and is called a permanent magnet. One which loses its magnetic strength after some time is called a temporary magnet. The Earth itself behaves as a magnet and has north and south magnetic poles situated close to the geographic poles. A magnet can be divided into small domains. In an unmagnetized material, the domains are not aligned, whereas in a magnetized substance, they are. Magnets are normally shaped as bars or horseshoes. The region of influence which surrounds a magnet where the magnetic force acts is called a magnetic field. The simple rule for a magnet states that like poles repel and unlike poles attract. Thus, two north poles will repel and a north and south pole will attract. The force of attraction or repulsion is inversely proportional to the square of the distance between the two poles. The total number of lines in a magnetic field is called a magnetic flux. The symbol representing it is the Greek letter phi. In the SI system, the unit for the magnetic flux is the Weber, or WB. Flux density B is the flux per cross-sectional area, and B is equal to phi divided by A, the cross-sectional area, and expressed in Webers per square meter, or Tesla. Thus, phi is equal to B times A. Let's look at an example. A flux density of 0.7 Tesla is constant over a total area of 4.5 square centimeters. Calculate the value of the total flux. A is equal to 4.5 square centimeters, which is equal to 4.5 times 10 to the minus 4th square meters, and B is equal to 0.7 Tesla. The total flux, phi, is equal to B times A, or 0.7 T times 4.5 times 10 to the minus 4th meters squared, which equals 3.2 times 10 to the minus 4 Weber. Let's now turn our discussion to electromagnetism, motor effect, and magnetomotive force. When magnetism is created through the use of electricity, the result is known as electromagnetism. A magnetic field is established around a straight conductor or a coil carrying current. The direction of magnetic lines of force can be found by using the left-hand rule. If we grasp the conductor with our left hand, the thumb will indicate the direction of current flow, and the fingers will show the direction of force. The symbols shown are used to indicate the direction of the field. The first represents the lines of force going into the page. Imagine looking at the back of an arrow. And the latter represents the lines coming out of the page. Imagine looking at the arrow pointing towards you. A force may exist in an upward or downward direction when the flux lines interact and a current is flowing between the two parallel conductors. The direction of this force is determined by the right-hand rule. Three directions are shown by the hand, each at right angles to the other two. The first finger indicates the direction of the magnetic field or lines of flux, the second finger the direction of current flow, and the thumb the direction of force or motion if the conductor moves. The magnitude of the total force F on a current-carrying conductor depends on the length of the conductor L in meters, the flux density B in teslas, and the current I in amperes. Thus, the force in newtons is equal to B times L times I. The process of conversion of electrical energy to mechanical energy is called a motor effect. Magnetomotive force, MMF, is the magnetic equivalent of electromotive force, EMF, and is designated by the script F, as the latter creates a current I, and the MMF creates a flux phi. The equation for MMF is F is equal to N times I and is expressed in ampere turns. Let's look at an example. A conductor 50 centimeters in length is placed at right angles to the direction of a uniform field whose flux density is 0.7 T. If the conductor is carrying a current of 4 amps, what is the force exerted on the conductor? Force is equal to B times I times L, or 0.7 Tesla times 4 amps times 50 centimeters times 10 to the minus 2 meter, which is equal to 1.4 Newton.